Welcome to the course of heat transfer. In the last class, we have discussed some of the numericals pertaining to composite wall. So in today's class, we will solve some more problem related to the composite wall again, but different criteria. Now let us consider this problem. An insulated freezer is designed to operate with an internal air temperature of minus 20 degrees Celsius and the external air temperature is 25 degrees Celsius. The internal and external heat transfer coefficients are 12 and 8 watt per meter square Kelvin. The wall of the freezer consists of inner layer of plastic with the K is equals to 1 watt per meter Kelvin, 3 mm thick, and outer layer stainless steel, K is equals to 16 watt per meter Kelvin, and thickness is 1 mm. A layer of insulating material with a K 0.07 is sandwiched between these two layers, and the thickness of the insulation required to reduce the convective thickness of insulation required to reduce the convective heat loss. So it means that so if we understand the problem, so this is the inner material with the K 1 watt per meter Kelvin. This is the insulation, this is the outer material. Now he has given, so this is a freezer, means the temperature at this point is much lower compared to here. Yes, heat will be flowing from this point to this point. Okay, and these acts as a resistance. He has asked us to calculate the thickness of this insulation, and he has given the heat loss is 15 watt per meter square. Okay, now if you see the diagram with the resistive diagram, it appears like this. So we have 3 conductive resistances out of plastic, insulation as well as steel, and 2 convective resistances, R5 and R1. Okay, here is a freezer, so here is the outside temperature. So temperature at this point is obviously higher compared to this. The heat will be flowing from this point to this point. Now from steel to plastic, precisely. Now while transferring, we have 1 convective resistance here, 1 more convective resistance here. So R1 is nothing but 1 over H into A, but area is considered to be 1 because the heat flux is given per meter square, means area is 1. So R2 is nothing but L by K, you know that, and the thickness of this steel material is given, and corresponding K value is 16. You get 6.25 into 10 to the power minus 5 meter square Kelvin per watt. So general resistance unit is Kelvin per watt, as it is per unit area, it will be meter square Kelvin per watt. Similarly, R4 R4 is L3 divided by K3 into 1. K3 is 1, so it will be 0.003. R5 1 over H2, this is 0.0833. Now we need to calculate this width. What is the thickness at this point? Now we know total heat loss, we know total temperature difference, we know some of the resistances, okay, excluding R3. If we substitute R3 as L2 by K2, K2 is also given 0.07, we will be getting the value of L2. It is that simple. Now the same thing is done here. The heat flux Q, it is given as 15. Change in temperature, 25 is outside, minus 20 is inside. We need to take the difference, so minus of minus will get added. The only unknown is R3. So R3 you will be getting 2.788, but R3 is nothing but L by K2 into A. Again A is 1, so L2 will be this multiplied by K2, which is 0.195. It is in terms of meters, or it will be 195 mm. Now this is one more problem with a given diagram, again based on composite wall only. The difference is at this point these two materials are not in series, so hence you need to consider these two are in parallel. This is the resistance diagram, so you can see RA, RB and RC are in parallel. RD and RE again they are in series. Now you need to get the equivalent resistance corresponding to this, that is 1 over R equivalent is equals to 1 by RB plus 1 upon RC. If we go by the problem statement, so determine the heat transfer through the composite wall as shown in the figure. Take the conductivities of A, B, C, D and E as 50, 10, 7, 20 and 30 watt per meter Kelvin respectively, assuming one-dimensional heat transfer. So this is given. All right, in the figure you can calculate the area. This is 50 centimeter. What could be this dimension? This dimension is nothing but the sum of 25 and 20. So that is the dimension of this slab. So 50 multiplied by 45. So that is for slab A, slab D as well as slab E. That is the area. But for slab B and slab C, the area is 50 remains same, the width, whereas the height differs for B and C. For slab B, the effective area is 50 by 20, whereas for slab C, it is 50 by 25. So the thickness of individual slabs is given 5 centimeter, 10 centimeter, 5, 5. Okay. Now what you need to do is you have to calculate the heat transfer. You know that heat transfer is total temperature drop divided by total resistance. So resistance at this point can be calculated. So this is the thickness L over K into A. Area is nothing but 50 multiplied by 45 into 10 to the power minus 4. So that comes around, yeah, over here. So that is 0.225 meter square. And that is same for D as well as slab E. Okay. Similarly, area for slab B and C is 20 multiplied by 50 and 25 multiplied by 50. So 0.1 and 0.125 meter square. Rest is same. You need to calculate resistance L over Ka only conductive resistances are there. To calculate RA, RB, RC, RD and RE. Now here we need to calculate the equivalent resistance out of B and C, that is 1 upon RB and 1 upon RC. So if you calculate, the equivalent resistance is 0.0533. So this will be in series with A, D as well as E. So this is taken here. This is RA, RD and RE. So change in temperature is 700. So if you divide the total resistance to 700, you will be getting 9.18 kilowatt. Moving to the next problem. This is little important because this is with heat generation. Okay, square plate heater 15 by 15. So this is the heater. Okay, is inserted between two slabs A and B. A is 2 centimeter thick, so this is 2 centimeter thick, and it is having a value of K as 50 watt per meter Kelvin or degree Celsius. And slab B is 1 centimeter thick. The value of K is 0.2. The outside heat transfer coefficients on side A and side B are 250 watt per meter square Kelvin. It means that at this point, convective heat transfer coefficient is given, which is 200, and at this point, convective heat transfer coefficient is given, which is 50. The temperature of the surrounding air is 25 degrees Celsius. If the rating of the heater is 1 kilowatt, find the maximum temperature in the system, outer surface temperature of two slabs. Okay. Now we will understand the problem. Now what is given? You have a heater whose dimension is 15 centimeter by 15 centimeter. It is placed in between two slabs A and B. We will assume both the slabs are having same dimension as that of the heater. They are also 15 by 15. Now this heater is having a rating of 1 kilowatt. It means Q is given as 1 kilowatt or 1000 watts. You need to calculate maximum temperature and the outer surface temperature. The maximum temperature will be over here. Okay, and outer surface temperature at this point for A and at this point for B. Now on both sides you have air, means convective heat transfer is occurring. Now if I ask you how many resistances are there with A and the left side, they are 2. Okay, so you can see here. So this is the maximum temperature. You have one conductive resistance, you have one convective resistance. On either side, you have one conductive resistance and one convective resistance. So what is asked? So T max is asked. So this is the source. So your heat will be flowing from this point to this point. So in this, okay, while flowing, so this material offers some resistance and this air offers some resistance. The resistance offered by the material is L over Ka, where La is the thickness, K is the thermal conductivity, area is 15 by 50. And 1 over Ha, H1 is the convective heat transfer coefficient corresponding to this region. So that is given as 200. At this point, it is given as 50. Calculate resistances. Now here, total heat flow is nothing but heat flow through slab A plus heat flow through slab B. Now, how much of heat has been flown from slab A? The change in temperature, T max minus TA, you can see here, T max, this is a T max, minus TA out of two resistances through slab A. Similarly, T max minus T2 or TA out of two resistances, correct? Now, so this is T max minus TA out of two resistances plus T max minus T2 out of two resistances. Now area is known to you, 15 by 15. You take it out and you calculate the fraction of this. So this comes out to be 199.47 multiplied by, this is the area, multiplied by T max minus 25 by 25 because that is the air temperature. So you need to equate it to Q value, that is 1000 watt given. So only unknown is T max. So if you calculate, comes out to be 247.8 degrees Celsius. Next, coming to the second bit of the question, that is surface temperature. So considering this to be steady state, the amount of heat transferred through slab A is nothing but T max minus T1 over the corresponding resistances. See here, surface temperature is nothing but at this point. You can consider T1. Now, while flowing from this to this, what is the resistance? This one. We will not consider this resistance because we need temperature at this point. So we know maximum temperature. Just now we calculated. We need to know this temperature. So corresponding to that, this is the resistance. We will be considering only conductive resistance. So if you do that, you will be getting T1 as 231 point. The same you can do with T1 minus TA divided by 1 over HA. How? Because you know, you need to know this temperature, but you know ambient temperature. So for this to this, heat is flowing. For this heat transfer, this is the resistance, which is convective resistance. You can solve either by considering conductive resistance or by convective resistance. So in both the cases, you will be getting T1 as 231.3 degrees Celsius. Similar is the case with T2. You can calculate either by considering conductive resistance or by convective resistance. You will be getting T2 as 88.6 degrees Celsius. Next. So this is on sphere. The problem statement goes like this. A hemispherical oven, 600 mm radius, has inner surface temperature of 820 degrees Celsius. The oven is lagged with 100 mm thick fire brick of conductivity 0.27 watt per meter Kelvin. Surrounding this is a magnesia layer, 50 mm of conductivity, 0.045. So this is 50 mm. First layer is 100 mm. Corresponding thermal conductivity is 0.27. Next is 50 mm. Corresponding thermal conductivity is 0.045. Compute the heat loss. The outer surface has heat transfer coefficient of 8 watt per meter square Kelvin. and the ambient temperature is 20 degrees Celsius. Now here, so this is the diagram corresponding to the given problem. You have a sphere over which you are mounting an insulating layer of 100 mm thick. Over that, you are mounting one more insulating layer, which is of 50 mm thick. Now, the sphere is having a radius of 0.6 meter. So this, from this point to this R1 is 0.6 meter, over which we have mounted an insulating material. So R2 becomes 0.7. Similarly, R3 becomes 0.7 plus 0.05, so 0.75 meter. Now, inner temperature is 820 and outside temperature is 20 degrees Celsius. And it is also given there is a convective resistance at this point. So, whose coefficient of heat transfer is 8 watt per meter per cap. Now, how many resistances are you getting here? So, one is out of this material, one more is out of this material, and one more is out of convection. So, total 3 resistances, correct? So, one out of this material 100 mm thick, one out of 50 mm thick, so one out of convective resistance. So, 3 resistances in total. Now, as it is a hemisphere, you will be having, so heat transfer out of hemisphere will be half of the full speed. You know that. Now, you need to calculate the heat transfer. So, for that, total heat transfer out of hemisphere is half of total change in temperature divided by summation of summation of resistances. Now, how many resistances? 3 resistances. First one is conductive resistance. Conductive resistance R2, R3 is convective resistance. As it is a sphere, the conductive resistance is given by R2 minus R1 divided by 4 pi K R1 R2. Now, see here, so this is R1, from this center point to this point is R1, from center point to this point is R2. Now, remember like this, outer radius minus inner radius divided by 4 pi K R1 R2. Similarly, what is the conductive resistance for this material? Outer radius, which is R3, minus adjacent radius, that is R2. So R2 will be, capital R2 will be R3 minus R2 divided by 4 pi K2 R2 into R3. So if you calculate, so you will be getting the value of 0.0702 Kelvin per watt for R1 and R2 0.1684. And as I told you, R3 is nothing but convective resistance 1 over HA. Okay. So area is surface phenomena 4 pi R square. R is nothing but R3. You will be getting 0.0176. You don't need to make this half at this point because you have considered here itself. Okay. Now, if you calculate, the heat transfer out of hemisphere will be 1.56 kilowatt. Now, the second bit of the question is interface temperatures. So, in order to calculate, you can use this equation. So, corresponding change in temperature divided by corresponding resistance. If it is Ti with T2, so corresponding resistance is R. So, it is multiplied by 2Q because whatever heat transfer you have calculated, it is corresponding to hemisphere. So, you will be getting a T2 as 600 degrees Celsius. Similarly, T3 as 75.19 degrees Celsius. You can see here. So T1 should be greater than T1 should be greater than T2 should be greater than T3 should be greater than outside temperature. So here T1 is 820 or Ti. T2 you calculated around 600, T3 75, and this is, so T1 over here, T2 600, 75, this is 20. So heat is flowing towards the lower temperature region. So this problem is similar to the previous, but this is based on cylinder. The conductive resistance for cylinders is ln R2 by R1 divided by 2 pi KL, where R2 is the outer radius and R1 is the inner radius of the cylinder. Sometimes in the problem, he will be giving you the diameter. See, in this problem, he has given diameter. You should convert it into radius. So this is an area where many students do mistake. So please be aware whether the given dimensions are diameter or radius. So need to be careful. So he has asked heat transfer per unit length. So this is very simple problem. I think you can do that. At the same time, he has asked interface temperatures. It is similar as we have done for the previous problem. Now we will consider this a standard cast iron pipe. Again, this is on cylinder. The inner diameter is given and the outer diameter is given. So inner diameter is 50 mm, outer diameter is 55 mm. Is insulated with 85% magnesium insulation with a K 0.02 watt per meter Kelvin. Temperature at the interface between the pipe and the insulation is 300 degrees Celsius. Pipe and the insulation. Okay. The allowable heat loss through the pipe is 600 watt per meter. So Q per unit length is given, watt per meter. Okay. K of the pipe, and for the safety, the temperature of the outside surface of insulation must not exceed 100 degrees Celsius. Now determine the thickness of minimum insulation required and the temperature of inside surface. Now this is a pipe having diameter 50 mm, which is inner diameter, and outer diameter is 55 mm. You consider the radius, so that becomes 0.025 meter and 0.0275 meter. So K corresponding to the pipe material. Okay, now we have insulation Ka as well as Kb. So Ka is 20 watt per meter Kelvin. Kb is 0.02 watt per meter Kelvin. So T2 and T3 is given. Now, as I told, heat transfer per unit length is given as 600 watt per meter. Now, if you consider Q by L is equals to 2 pi Ka into T1 minus T2 divided by corresponding resistance, or Q by L is equals to T1 minus T2 divided by conductive resistance in case of cylinder, which is ln R2 by R1 or ln of outer radius divided by inner radius upon 2 pi K into L. K corresponding to duct material and L, we have considered it to be 1. Now if you substitute the values, Ka is given, Kb is given, T1 you need to calculate. Here T2 is given, T3 is given. So you can, here you can calculate R2, R3 by R2. R3 by R2, yeah, you got here R3 by R2 as some value. R3K is nothing but this multiplied by this value. It is 28.7 mm. Now the thickness required for insulation is outer radius minus inner radius. So it comes around 1.2 mm. Now the second bit is calculation of temperature. So considering Q is equals to 2 pi K into T1 minus T2 divided by ln of R2 by R1. So you will be getting T1 as 300.45 degrees Celsius. So remember, whenever surface temperatures are asked, you take the temperature drop corresponding to that and the resistance corresponding to that slab. So that gives you the intermediate temperatures or the surface temperatures. Now we will solve one more problem on sphere. This could be the last problem, I think. So determine the rate of heat flow through the spherical boiler, which is 2 meter in diameter. Again, diameter is given. It is 2 meter and 2 centimeter thick steel with a K value. The outside surface of the boiler wall is covered with asbestos. It is an insulator. Value of K is 0.116 and 5 mm thick. The temperature of the outer surface and that of the fluid inside are 50 and 300 respectively. So this is, first one is inside, outside and inside. So outside this is 50 and inside this is 300. Take the inner film resistance as, okay, 0.0023 Kelvin per watt. So directly resistance is given. We can consider one resistance. Now how to solve this? Same procedure. So first you calculate radius R1, then over which you have mounted some material of thickness 2 centimeter. So that becomes R2. So R1 is 1 meter. Okay, because diameter of the sphere is given. So this is the sphere inside. So dotted line indicates the resistance out of air inside. So this is first material. So this is second material. So first material thickness is 2 centimeter and second material thickness is 5 mm. Okay. Then R2 will be 1.02. What is R3? R2 plus thickness 5 mm. So 1.02 plus 0.005, 1.025. So that is R3. The thermal conductivity is given for this layer as well as this layer. This is 58 given in the problem and this layer is 0.116. So if you see that we have first convective resistance, conductive resistance, total 3 resistances. So total heat transfer is nothing but T1, which is 300 minus outer temperature 50. 250 is the temperature difference. Okay, so this part he has directly given 0.0023. R2 minus R1 divided by 4 pi K. You can consider Ka here 58. R1, R2. Keep all the parameters in SI unit. You will be getting